Welcome to our audience and our audience online. I'm John Grant, the chair of the Center for Earth and Planetary Studies here at the Smithsonian's National Air and Space Museum. The Center for Earth and Planetary Studies is active in planetary research, in terrestrial planets in general, but in Mars in particular. We have involvement in a variety of missions as well as scientific research programs. I'm delighted to be standing here in the Moving Beyond Earth Gallery today to welcome you all to a Mars program update. There's been some very exciting results related to Mars research in the past 10 years or so, and we've got a three-part program that's geared towards bringing those results to you and telling you where we're going to be going in the future. I'd also like to welcome the Stuart Hobson Middle School, who's in attendance today, and also the Whittier Education Campus STEM School, who's also in attendance. I'd like to point out that this is going to be broadcast live on NASA TV for those of you that are here in the audience. And what I'd also like to do is take a second and mention to you that we've got some of the leaders in Mars research and the Mars program here today to talk to you. Basically what we're going to do is have a three-part program that's going to tell you something about what we've done and where we're headed. The first part of this will be a discussion of recent discoveries. Basically, we've been out following the water, and now we're going to tell you what we found. Then we'll take a quick break and we'll talk about an update of the mission plans that are ongoing but also that are scheduled for the future. And then third, we'll take a little visit to what and where we hope to go in the future and the kinds of discoveries that we think that we can make. To start us off and head us on down this road, I'd like to introduce Doug McQuitchen. He is the Mars Program Director over at NASA headquarters. Doug.
Thanks, John. Well, good morning, everybody. It's great to be here. It's a very exciting opportunity here. John was talking about just a three-part program, but actually there's an enormous amount of information and some very exciting things coming in these three sessions. We're here for two main reasons. One of those is we've had about 10 years now of human presence on another planet. So we've been on Mars with the Mars Exploration Program since 2001. Consistently. It's pretty much a permanent presence, both with spaceborne assets as well as surface assets. We have never done this on any other planet anywhere, obviously, other than Earth. So that's a pretty big milestone, it really is. The second thing that we're here for is transition. This is a major transition point in the program. We've been, as John said, following the water. We've been trying to understand the history of water on this planet and why our sister planet looks so different today than the Earth looks. We've learned a lot about that, but now we're ready to move to a new phase about whether life ever existed on that planet or does it exist today. You're going to hear a lot about that too. So that's a major transition point. We also have a new activity here with the Europeans. We have a partnership beginning in the middle of this decade. We actually are going to do our missions in a joint fashion. The Europeans and the Americans are going to go to Mars jointly as often as we can. So you'll hear from my ESA colleague about that a little bit today. We've also been on the planet twice as long as Lewis and Clark spent exploring the Northwest. That's interesting and it's important because just like Lewis and Clark, who spent about 6 years exploring, we've been there for 10. They didn't see everything. They didn't find everything. So they were looking for the Northwest Passage. They found the Pacific, but what they didn't do, they never saw the Grand Canyon. You know, they never found the deserts of the Southwest. They never got to Mexico. There was a lot they never saw. While we've seen incredible things, we've done incredible things, we've gone places we never expected to go, and you'll hear from Steve Squires about how far we've gone with the MER rovers, which we never expected. There's plenty left to see. There's a lot we haven't seen yet and we want to find. Just like Lewis and Clark, we've taken a lot of this information, taken the data, we've interwoven the data, we've interpreted the data, and we've created a story of what's happened to Mars. You're going to hear that story initially from Jack Mustard and from Steve Squires. Then you're going to hear about how we figured this out from myself and Marcello Corradini. After that, you're going to hear about where we're going to go. You'll hear that from Mary Wojtek and Jen Eigenbrot and Michael Meyer. John Grant will be back up here. If we get that one slide up, please. So the important thing is this transition. We're going to make the transition from following the water to seeking the signs of life. And in the discussion today, there's going to be a little bit of something for everybody. Those of you who like science, hopefully some of you guys like science. There'll be plenty of science in this. For those who like hardware and engineering kind of things, there'll be some of that. For those of you guys who like history, the reason history is important is we're making history. We've changed textbooks, and we're going to keep making textbooks. So you're going to hear about how history, in y'all's lifetime even, has been made. And you're going to hear it right here, and you're going to hear it from a lot of the folks that have done this. So I hope you like what we have to say. I hope you like how it goes. I hope you walk away thrilled, excited, and want to dig in more about planetary science. And so let's get started with the first panel. So I'm going to reintroduce, wherever he is, John Grant, senior scientist here at the Smithsonian Institution, as a moderator for the first panel.
Thanks, Doug. Thank you very much. As Doug has said, there's been a decade of exploration of Mars. It's been a measured approach to understanding Mars, and what we've discovered through this approach is that Mars is even more interesting than we could have imagined. And so to give you an update and provide some details on some of the exciting discoveries that have been made over the past 10 years or so, I'd like to introduce our first panel. First, I'd like to introduce Dr. John Mustard. I've known John since we were graduate students back at Brown University, where he is now a professor. John is a preeminent Mars scientist. He's involved in a variety of orbital missions related to Mars and understanding about its evolution, its mineral composition, its geologic history. Next, I'd like to introduce Dr. Stephen Squires. I haven't known Steve quite as long as I've known Jack, but our 90-day mission now is in its 7th year. This is the anniversary of the MER landings on Mars. Steve is a professor at Cornell University. He's the chair of the Decadal Survey, which will be coming out in the near future, sponsored by the National Academies to have a look forward at the missions that could be planned. And he's also the PI of the Athena science payload on the Mars exploration rovers. Gentlemen?
Thank you.
We'll start with Jack providing an update on some of the recent discoveries on Mars.
Thanks, John. Looking forward to talking to you all here today as well. It's a pleasure to be here and to see you all. So if I could have the first slide. As we've talked about, it's been a decade of intensive exploration of Mars. But it's really been going on for a long time. And Mars has been in our mind and imagination for a long time. This is a book from the turn of the last century about the exploration of Mars, in which entire civilizations were encountered, different types of beings, etc. And it really fueled our imagination about why we would want to go to this planet. But the reality was, could I have the next slide, please? One that was very different. Despite the expectation of entire civilizations, the finding was that there were, in fact, a very dynamic and interesting planet. One that, as we look at this graphic here, on the left-hand side, we can see that it has polar caps. So it actually is very similar to the Earth in that sense. It has poles that was very cold, and in that polar cap there are layers that can be identified, and those layers indicate change with time. From a geologist's point of view, that is gold, because that allows us to see what is the record of change on the planet. But as we look deeper, we can see that there was evidence for giant canyons, potentially ice flow that was flowing there, and maybe even indications that there might have been oceans. But the reality was that this was all very much in the past. So the question we have is, gosh, this has a lot of Earth-like characteristics and qualities. And that's very exciting. But is it Earth-like? And the key question is, if it was Earth-like, did life ever get a chance to get going? And was there life here today? Could I have the next slide, please? Well, a rock that was found actually in Antarctica on the ice sheet was studied intensively by scientists. It was determined that it was from Mars, and it had these indications that it may have had life in it. And this is one of the pieces of evidence that was used, was these morphologies or shapes that were indicative of potentially life forms. Turned out that it wasn't quite so simple. And this sparked an entire exploration of the planet Mars in a very systematic way. Could I have the next slide, please? And instead of simply jumping to Mars and saying, where's the life forms, we said we have to look at this very carefully. And we have to start from a very, I wouldn't say simplistic, but start from the beginning. And the key aspect for sustaining life is water. Where is the water? And what form is the water? So that's where we started. And this graphic gives us a short summary of what is the distribution of modern water. Where's water today? And what we find on the upper left-hand slide of this graph is in the colors of blue is where the high concentrations of water exist frozen. It's frozen just beneath the surface. In the middle region of Mars, this map of Mars, you can see where it's got the orange tones. That's really, really dry. So this is great. It shows us where the water is. And we sent a spacecraft, the Phoenix spacecraft there, just a couple of years ago. On the right-hand side of this slide, where we landed on one of the places where we predicted water ice to be, they landed. In fact, the rockets of the spacecraft exposed water ice right at the surface. So this is science at its best, where we make a prediction, we're able to go to the surface and confirm that and learn a lot about the planet along the way. And in addition, we're using sophisticated tools such as radar, which is we use for weather sensing on the Earth. If we look at the planet with that, we can see that there is buried water in a lot of different places. Could I have the next slide in this? But that's water on Mars today. What about its past? Well, we can use models and our best understanding of how the planet works to predict where water has been in the past. And this view of Mars maybe 500,000 years ago shows that water was taken from the polar regions and distributed in this mid-latitude region. And that's a prediction. And the question is, did Mars have these ice ages, and did it leave a record of that? And does that tell us how Mars operates in its climate and water today? So if we go to the next slide, in fact, the recent cameras and instruments on the Mars Reconnaissance Orbiter found indications that that past, where water was distributed throughout these middle regions of the planet, in fact existed. So this graphic in the middle shows the depth in color to the ice table. Where is the ice below the surface? Where red indicates very deep, 10 meters or so, and blue is very close. So that's a prediction. And those black dots show where impact craters landed in the last couple of years, and they actually excavated some of this buried ice. So that is a fantastic, again, prediction. You know what's important about that? Is it brings the water ice from the poles much closer to the equator. This is great, because it's now becoming more accessible to the rovers that we have, and perhaps humans in the future. So we're making it more accessible. Could I have the next graphic, please? Now, as we use some of our orbital assets, you'll see that we're learning more and more about where water may form. This is, again, using a radar in the upper right, which can fire electromagnetic waves at the surface, and by measuring the return, we can predict maybe what's buried. And in the upper left-hand side of this graphic, you can see that we predict that there was buried ice based on the radar. And the lower left image in that graphic shows one of these features on Mars where you can see it looks like something has flowed out off this mountainside. And in fact, using this radar, it shows that there is water ice, and in the blue in that map shows this is distributed over large regions. Not as much as the other water ice, but it's, again, moving it closer to the equator, moving the accessible water ice closer to the equator where rovers and astronauts, et cetera, could have access to it. And it's showing this record of climate change that is preserved on the planet. So could I have the next slide there as well? And I'm going to step through this a little more quickly because we can actually show with our orbit where we find the frosts of carbon dioxide and water ice. And in the graph in there, it's showing in the blue arrows where we can see what's called absorption features in a measurement of reflected light. And on the bottom is this is in a scale of wavelength. And with those features from our orbital data, we can actually map where frosts are of different types of ices, and in this case, carbon dioxide. So when we map those, which is showing us in that one map on the right, where deposits of frost form, this is just carbon dioxide frost. Next slide, please. We can see in this map of Mars, in the black dots is where we see this frost to form, but in the red line says where it should be. Based on our models, it should be in all these different places. Why don't we see it everywhere? The reason we don't see it everywhere, could I have the next slide, please, is that there's something buried which is warmer than the ice than warmer than what would sustain carbon dioxide frost. And this map shows that we have a dry layer on the surface, which gets quite cold and supports carbon dioxide frost, but below it is something that keeps it warm, which in this case is buried water ice. So in that map there, you can see where there's purple. That means there's no buried water ice, but everywhere else there's actually water ice very close to the surface. And this, again, brings ice closer to the poles for us. Could I have the next slide, please? But one of the things that we've learned, okay, so that's modern water, and it's frozen, and it's not sustaining large civilizations, but there might be microbes potentially buried. But when we look at the history of water on Mars, we have even a more dynamic story. This graphic here, it's a little bit complicated graphic, but on the bottom you can see the numbers going from 0 to 4.5. That's time, where 0 is today. 4.5 is 4.5 billion years ago. When we look at Mars, we can see that Mars has gone through various stages in its evolution. In the earliest period, the first billion years, it's called the Noachian. It was wetter, we think, based on geology. In the middle period, it became a different planet with more volcanism. And then this Amazonian period, the last 3 billion years, has been this cold, dry place where there's glaciers. And along the top of this graphic, we see there's a mineralogy that goes with this. What types of minerals form? And from that, as a geologist, we can tell what was the habitability. In other words, was it a good place to be a microbe or a human? Or was it a difficult place to live? And you see in that first period where clays form, it's a neutral pH, but you reach this middle period where it becomes acidic, where it becomes very difficult. And it's one of the great discoveries of the rovers and others that I'm sure Steve will be talking about, showed us that it was a much more challenging environment to live. Leading us to the present, to live at the surface has become really difficult to live because there's not a lot of liquid water around. So something absolutely phenomenal happened in that time frame as we go from clays, when it was neutral, to sulfates, when it became acidic, to very dry. Something happened to this planet. And we're not quite sure what, and it's one of the things we're really interested to find out because it changes the suitability of a planet for its habitability. So if we go to the next slide, this is an example of one of these environments that may have sustained the conditions where if life had been present, it could have been sustained. So in the top of this graphic, we see a topography map of a portion of Mars, and you can see the large circular region in the lower right-hand side of this graphic. And in the bottom, we actually show that we can trace river channels that flowed into that circular region, which is an impact crater. And in fact, it has 2 inlets and 1 outlet. So that was a lake that sustained itself for a while. And in that lake are these 2 colored regions, which we call the northern delta and the western delta. And I'm going to show you right now a close-up of that in the next slide. And in that, we can see it's actually got the shape that you would expect of a delta on the Earth. It's dried up now, so the water flowed into this lake, formed a delta. And the amazing thing with our orbital assets, with our orbital instruments, we can determine the minerals. And in there, we see the minerals of clay and carbonate, which for a geologist is really important because it says that those were the types of minerals where that record the conditions, and if there had been life, they would have captured the evidence of that might be kept here for future generations or us here today to go and measure and understand what was going on. Could I have the next slide here? So this map shows in the middle of the Grand Canyons of Valles Marineris, there are these deposits in these sedimentary units in the middle. These are quite large, in which the sulfate minerals form. So if you all take a bucket of seawater from the ocean and let it dry out, you will form these sulfate minerals. That's what appears to have happened on Mars. And here in the middle of the planet, we see it drying out. So it went from a nice clement planet, so something happened and changed it. And could I have the next slide, please? And what were these habitable environments like, and what are the most promising environments where we could seek the signs of life is one of the dramatic questions we're interested in. In this slide at the bottom, it could be weathering, rainfall at the surface, or it could be like in a hydrothermal system with hot water or hot springs. And in the top part, those are the rocks that we're going to go at, but we need to go and examine in greater detail to understand this better. So could I have the next slide, please? And with the upcoming activity of the Curiosity rover to be launched to Mars very shortly is to examine these types of places, and John Grant and others will talk about the compelling sites that we're going to go to. One of them is this impact crater called Gale, and in Gale has a giant mound in the middle, and that mound is a sedimentary mound. And what's important for us geologically and for the planet is you can see the green line where the rover might traverse in that to examine this place. Could I go to the last slide here? And what Curiosity can do then is go up this mound of sedimentary rock. And the important thing is the first part of its investigation will be in this world which has clays and sulfates. And remember that timeline I showed, the first part was clays, which is a more habitable type environment or a nicer place to live than the upper part where sulfates, where it could have changed to an acidic planet. And this is just one example of among the options that MSL can go, or Curiosity can go, but it does allow us, now we have very focused questions to try and address here about the history of Mars and how it could have evolved and provided a habitable or uninhabitable environments for us to look in. So it's been a pleasure to try and bring you up to date a little bit of some of the great discoveries that we've been having here on Mars, and I'd like to pass it back to John.
Okay, thank you very much, Jack. What we're going to do now is hear a little bit about a couple of locations on Mars where we've been getting up close and personal with some of the rocks, and how that fits into the story that Jack has just laid out before us about the history of Mars and where water occurs. And I'll point out that after Steve gets done describing some of these recent results from the Mars exploration rovers, we will have time for question and answers. So you'll have a chance to ask some of the questions that you might have of our speakers. Steve.
All right. Well, just about exactly 7 years ago, 2 explorers landed on the surface of Mars. They are robots. Their names are Spirit and Opportunity. They're identical twins, more or less. They're about this tall, about 5 feet tall. They're about this wide, about 6 feet wide. They weigh about 350 pounds. They drive really slowly. And over the course of 7 years, the 2 of them have covered something like 20 miles together over the surface of Mars. They've returned many tens of thousands of pictures. You can find all the pictures out there on the World Wide Web. And they've told us an enormous amount about what rocks are like at these 2 locations on the Martian surface. Now, as Jack described, Mars today is a cold and dry and desolate world. If you went there, you would hate it. Okay, it's 60 degrees below zero. If you took all the water vapor in the Martian atmosphere and you condensed it on the planet's surface, you'd make a layer of frost that's like 1/100 of a millimeter thick. So it's a pretty miserable place today. But these data that we've acquired from orbit, the pictures, the spectra, they show evidence that in the past, Mars was different. It was warmer, it was wetter, it was more like Earth. And so the job of the rovers was to go to 2 places where we think there might have been water in the past and to try to learn what the conditions were like there by reading the story and the rocks. I'll start with Spirit. The Spirit rover went to a place called Gusev Crater. Jack showed you a graphic in which there was a big crater with a dry riverbed flowing into it. Gusev is like that. There was a lake in Gusev once upon a time. So we went there hoping to find sediments that were laid down long ago in a Martian lake. We didn't find that. What happened at this place was after the sediments were deposited, and I'm convinced those sediments have to be down there someplace, but after they were deposited, lava got dumped on top of this stuff. Lava erupted over top of the sediments and buried them. We didn't know that till we got there. It was kind of a bad surprise, actually. It was kind of a disappointment when we learned that. But what happened was, about 1.5 miles from where we landed, there was this beautiful range of hills that we named the Columbia Hills. They're named after the Columbia Space Shuttle. And because the rover has lasted so long, we were able to drive that 1.5 miles to the hills. And the hills sort of sit up like an island sticking up through that sea of lava. And they're made of totally different stuff. They're very ancient. And what the Columbia Hills do is they provide us with a window into the very ancient past of Mars. And with the Spirit rover, we were able to climb actually to the very summit of one of the tallest hills in the range. And we've spent years now exploring the Columbia Hills and looking at the story in the rocks. The story that these rocks tell of very ancient Mars is that it was a violent place. There were impacts where meteorites would come in from space and they would blow a big hole in the ground, dump rocks all over the place. There were volcanic explosions where lavas maybe came into contact with water and it flashed into steam and boom, blew stuff up in the air. So we see the remains of these violent events. It's a quiet place today, but it was a much different place back then. The other thing is that we see compelling evidence that there was water present and there were hot springs. We see a lot of evidence for what geologists would call hydrothermal activity. This is what happens when water comes into contact with hot lava. And you can get steam vents and you can get hot springs with water flowing out of the ground. One of the big discoveries, one of the biggest surprises, we found very concentrated deposits of silica. It's like opal, like the gemstone. This is the kind of stuff that can form in hot spring and hydrothermal environments. We found very concentrated deposits of this, and what it says is this is a place where hot water or hot steam came out of the ground. Now you can go to places on Earth today where hot water and hot steam come out of the ground and they're teeming with microbial life. Doesn't mean there was life on Mars necessarily, but this points to evidence of a former habitable environment, a place where life maybe could have taken hold on the surface of Mars. Another thing that we found was we found carbonate rocks. This was something that Jack mentioned too that's been seen from orbit. Carbonates is basically limestone. In our case, it was iron carbonates and magnesium carbonates, but we found concentrated deposits of carbonates, and what these point to, again, is water being present, and water being present with a water chemistry that's the kind of thing that could be suitable for life. So even though Gusev Crater is cold, dry, desolate today, it clearly was quite different and much more suitable for life in the past. Opportunity landed completely around the other side of the planet, 180 degrees around the other side of the planet, on a place called Meridiani Planum. Now, the reason we chose Meridiani as a landing site was that from orbit, we saw the signs of a mineral called hematite. Hematite's an iron oxide. It's a mineral that's present in rust. Okay, and it's a mineral that typically, not always, but usually forms in the presence of water. So it was like this chemical beacon visible from space saying, hey, come land here. We landed at Meridiani and we were just baffled. It was bizarre. On the soil in front of the lander, we actually landed in a little crater. There were these little, they looked like beads, little round things, 4, 5, 6 millimeters in diameter, and they were everywhere. We called them blueberries because they sort of looked like that. They're actually not blue, they're gray. And it turns out that they were embedded in the rocks. And the blueberries are made of hematite. This was bizarre. Nobody expected this. We drove over to the rocks and we found out that the rocks were sediments that had been laid down by wind, and in some cases by water long ago. You can see little ripples in the rocks that show that flowing water was actually at the surface here. The rocks are made mostly of sulfate salts. Jack said if you have a bucket of the right kind of seawater and you let it evaporate away, you can make sulfate salts. Well, that's what we see at Meridiani. So we see evidence of water below the surface. We see evidence of water near the surface. The blueberries, it turns out, are things that geologists call concretions. When water saturates the ground in some place, we find these on Earth. Typically forms in places where you have sedimentary rocks that are saturated with liquid water. There's some mineral that's dissolved in the water. It wants to precipitate out. And it finds a little nucleation point and it starts to precipitate. And it grows and it adds layer upon layer upon layer, making this little hard spherical nodule in the rock, sort of like the way an oyster builds a pearl, okay? And it makes these little hard nodules through the rocks, and that's what the blueberries are. So we've got this compelling evidence at Meridiani that there was water beneath the ground, that water occasionally came to the surface. Now, when we made this discovery, people made a big deal about it, right? Rovers discover evidence of water on Mars. Well, honestly, we've known that there was once water on Mars. If you want to talk about the space mission that discovered that there was water on Mars, you got to go back to Mariner 9 in 1971. That's the mission that discovered there was water on Mars. But what we've been able to do is we have been able to add layer upon layer upon layer of detail to our understanding of what the chemistry was like, what the environment was like. So for example, when we look at the minerals that are present in the rocks at Meridiani and we look at those sulfates, they actually tell us that the water was acid. You know, people say, we found evidence for water on Mars. Well, what we really found at Meridiani was evidence for sulfuric acid on Mars. You wouldn't want to drink this stuff. Okay, now there are organisms that can live in environments like that, but this would have been a very challenging place for life. All the discoveries I just listed, we made in like what, the first 2 months of a 7-year mission? And then we've been adding detail to it since then. To date, the Opportunity rover has driven something like 26 kilometers, so getting close to 15 miles across the Martian surface. If I could have the first graphic up. Opportunity is currently parked right on the rim of a spectacular impact crater. It's about 100 yards in diameter. We've named it Santa Maria crater. It's named after one of Columbus's ships. And if you look carefully in this graphic, you can, this is a picture taken from orbit, you can actually see the rover right there on the rim of Santa Maria crater. It's kind of cool to see our rover again. If you go to the next graphic, you'll see the view that Opportunity had from that spot. This is a spectacular hole in the ground. It was caused when there was an impact that formed, or an impact that took place on the surface. Rock from space comes and blows a big hole in the ground. The cool thing about craters is they provide us with access to rocks from below the surface that we can't get at any other way. We didn't bring a drill. We didn't bring a backhoe. We didn't bring dynamite. But Mars has dug these big holes for us in the form of impact craters. And the rocks get thrown out of the crater. And right now, as we speak, Opportunity is perched right on the rim of this crater, on the far side of the view that you see in this picture. And we're hunkering down to really start in detail measuring the composition of some of the rocks that have come out of the interior of the crater. Let's go to the next graphic. We have a very distant goal that we have chosen for Opportunity. Now let me stress, these things were designed to last for 90 days. They were designed to drive 600 meters, less than half a mile, over their lifetimes. We've gone something like 15 miles with this thing. If you look at this graphic, what you can see, there's a crater there named Victoria. We spent years exploring Victoria crater. Right now, you can see where Opportunity is, Santa Maria crater. It's so tiny that you can't even see it in this view. Where we are going is this crater called Endeavour. Endeavour is enormous. This thing is a monster compared to any of the craters that we've seen before. It's like 15 miles in diameter. It is a big hole in the ground. The rim of Endeavour crater is visible from where we are now. Let me show the next slide, the next picture. This is the current view. This is looking off in the distance, and like islands on the horizon, as an explorer is traveling across this sea of sand dunes and sulfate rocks, we can see the rim of Victoria crater, and it's now only about 4 miles away. Don't know when we're going to get there, but I'm starting to believe we're really going to make it. The cool thing about the rim of Endeavour crater, you heard Jack talk about clay minerals. We know by looking at it from orbit that there are clay minerals at the rim of Endeavour crater. And if we can make it, and I don't know if we're going to make it. I mean, we voided the warranty on these vehicles a long time ago. But we're going to try. We're going to try to get to Endeavour crater, and my goal is to actually get there before the Curiosity rover. Curiosity is being targeted to go to clay minerals, and they're going to get there, and they're going to do great stuff, but we want to do it first. So we're going to try. Anyway, we've got a spectacular mission still ahead of us. 7 years in, and still going strong, and I'm looking forward to seeing what we see. Thanks.
Thank you, Steve. So we've heard a little bit about recent discoveries, where water occurs on Mars, how it occurs on Mars. We've heard a little bit about how the rovers have been exploring Mars, and investigating where this water occurs. What I'd like to do now, as long as we've got our esteemed panel up here, is open this up for a couple questions from our audience and find out if folks have some things they'd like to ask. Yes. Could you please come up and use the microphone so that we can let everybody that's listening and watching online understand as well?
Has there been any investigation of the meteorology around Mars?
Has there been any investigation of the meteorology or the weather on Mars?
Sure,
Jack?
meteorology is a really important subject of what we learned. So we've been using a lot of orbital data from which we can determine where the dust clouds are, where the ices are forming and being removed. We can determine the temperature of the planet. And through the landers that have been on Mars over the years, we actually get weather stations on the surface. What we really need in order to do meteorology is a half dozen of permanent weather stations. And so that's one of the things that would be really exciting to have in our future rovers.
And let me say that we really care about the weather on Mars in a practical sense on our rover mission because we got solar-powered vehicles. And we really, really worry about things like dust storms. So I get a weekly weather report from the orbiters that tell us, what kind of weather we can expect in the week ahead for the rovers.
Other questions for our speakers? Over here, please. Use the microphone.
Professor Squires, I was curious if you could summarize, or actually all of you, we know there's a lot of water on Mars. Do we know enough to make some kind of quantitative assay about what sort of useful resource this water would be when humans explore it? I mean, from the water and some energy and the CO2, you can make rocket fuel, transportation fuel of various types. How much do we know that would underlie the use of that water as a resource for exploration?
Yeah, that's a very good question. Can you go to Mars and live off the land? The answer looks like it kind of might be yes. I mean, Jack described these impact craters where very fresh craters have excavated not very far below the surface and found compelling evidence for there being ice there. And it exists closer to the equator than a lot of people initially expected. So yeah, I think you can probably go there. You can excavate ice from beneath the surface. You're going to need a major source of energy. Okay, you're going to need something that enables you to dig, and digging into ice that is that hard frozen is hard to do. And then if you want to do things like make rocket propellants, yeah, you can split water into hydrogen and oxygen, and those are terrific rocket propellants, but it takes a lot of energy to do that. So the energy problem has to be solved, but is the resource there? Yeah. And is it accessible? Yeah.
Yeah, I think we're going to find, as Curiosity and other rovers go, that they're going to find the resource of water and other aspects are actually a lot closer and a lot more accessible than we currently think. There's been this constant oscillation in our understanding of Mars, where, as I showed, 100 years ago, we thought there were civilizations there. Then we thought it was so dry, all bets are off, there is no life. And then it swung back. So now I think we're zeroing in on what the reality is, but I think there's still a lot to learn. And I think we should take a shovel on one of these rovers, right? Because in some places, I think if we dig just below the surface, we might actually find something really compelling.
Yeah, we could dig trenches with the wheels. The problem with our rovers is because they're solar powered, they had to land close to the equator.
Yeah.
And close to the equator, you got to dig pretty deep. So we haven't been able to find any ice.
Question over here.
Yeah, you started to touch on my question. As I understand it,
Sure. Thank you.
As I understand it, the radiation environment's pretty bad on the surface, and plus with the dust devils and everything, it's almost, I guess, akin to sandblasting the entire surface. So answering the second part of our title, Seeking Signs of Life, how far down do you suppose we would have to dig to actually find evidence that there may have been life on the planet? And is that feasible with our current technology?
That's a good question. What he's referring to, the radiation environment, there are cosmic rays from space that constantly bombard the surface of Mars, and those can change the chemistry of molecules. If there are organic molecules beneath the surface, these cosmic rays can break chemical bonds and can basically destroy the evidence of what might have been life in the past. So you want to get deep enough that you're going to be able to find that stuff. you got to do calculations. You got to basically guess. And people have done these calculations, and the depths you get are not crazy deep. They're a meter or two. They're like this, okay? And so if you can find a way to get that far down, you have a chance of finding what you're looking for. The other thing is that you mentioned sandblasting. Okay, there are places where erosion takes place on Mars, and rather than having to drill or dig through a meter or two of stuff, you can rely on Mars to erode stuff away fast enough, faster than the cosmic rays can change the chemistry, and then you pick up rocks at that location. So I think our chances of finding rocks that have not been severely modified by radiation are pretty decent, but you got to go to the right place with the right tools.
And there are these new discoveries that have been coming out in the last several years, and we're debating this a lot in the community, is the presence of a trace gas, methane. We're all familiar with methane. On Earth, it is a part of the changing of the climate. On Earth, the primary source of methane is enteric fermentation. That's a fancy word for cows having a gassy day. So so this is really interesting, is the presence of methane. And as I say, it's controversial. In fact, in 2016, Europe and NASA together are going to send an actual spacecraft to try and look at these trace gases. So there might be the evidence of that today, where we might not have to dig as deep, letting the planet just give off its gases that we can sniff. So stay tuned, I would say.
Thank you. Question over here.
Yeah, so you talked about the different environments that that Mars could have been like in the past, and you had those 3 pictures up at the bottom of the slide. And I was wondering if there could be a possibility of an environment that we haven't seen before. So we're sort of basing it on stuff that we've seen on Earth. But are there characteristics that could have been on Mars however many years ago that we haven't seen before and could create a new environment that we don't know at all?
That's an awesome question and an awesome concept. And it's one of the things that we tend to work with what we know. And it's hard to kind of step too far beyond that. And we're trying to imagine different types of environments that may have supported life. And one of the interesting things, again, we use the Earth as our basis of knowledge, is as we expand the realm of where life can be possible, we're starting to understand on Earth the most extreme places you could imagine where life exists. And in fact, in the radioactive waste of some of our nuclear waste deposits, actually there's life that exists there. So we're learning that the limits of life go far beyond what we would have thought 20 years ago. And this is the kind of research that we need to do to think about possible environments. But those kind of questions are where we're heading, I would say.
Yeah, I worry about your question all the time, because we have to use our rovers to look at the rocks and try to interpret what we see, and we do our interpretation based on our own experience here on Earth. What we see at the rover sites is things that we recognize, minerals that we think we know about, like hematite, geologic features that we think we know about, like the little ripples in the rocks. So they're all basically familiar, but they're arranged together in ways that are uniquely Martian. Nowhere on Earth can you find a place that is like either one of those landing sites.
Okay, we've got time for just one more question, I'm afraid. I know there are others, but I'll turn it over here for our last.
You showed a slide that had the much larger polar caps, which I think is associated with the obliquity cycle. My question is, what's our current understanding briefly of the obliquity cycle? And specifically, in 10,000 years or 100,000 years, will we be warmer, wetter, or will we be colder, drier, or what?
On Mars. On Mars, right, so because there's the Earth. Well, it's an amazing, new results have come out about how what he's making reference to is what's the tilt of the planet. This is one of these weird things about Mars and the Earth. Mars and the Earth have the same tilt, more or less, today. But 100,000 years, maybe 5 million years ago, the tilt of Mars was quite a bit more, like 45 degrees. And this, what happens is it causes the poles to change their size as they move. The water ice is evaporated from the poles and moved. So we have very good calculations of how the tilt of Mars has changed. And now it's up to the models to then predict where the water would go as a consequence. But it is an absolutely amazing thing. The amount of tilt that we've had on the Earth and how that's led to ice ages, on Mars, that tilt has been so much greater. And so many different things have come from that.
Okay, I'd like to take a second and thank both of our panel members here for a really exciting update on Mars discoveries. Thank you, Jack. Thank you, Steve. We're going to move on to the second part of our three-part program at this point. And to kick that off, I'm going to reintroduce Doug McQuitchen, who's going to introduce the second set of discussions and tell you a little bit about upcoming Mars missions and what's in store. Doug.
Thanks again, John. Okay, I'm back. So you've heard what we've been finding. And here in a moment, you're going to hear from myself, and as soon as we get a mic on Marcello, you'll hear from my ESA colleague about how we find this stuff out. How do we see it? You've seen the images, you've seen the pictures, you got a little glimpse of opportunity there in that panorama. But we'll show you a little bit more about what we do and how we do it. So can I get the first slide, please? Yeah. So I said we've had a permanent human presence at Mars for the last 10 years. Well, you know, Steve is one of those main people living on Mars most of the time. He gets the weather reports, and, you know, most of the things he looks at is not out the window but on his screen, which is Mars. So we've got a lot of people that kind of live this, and we've done that through all these missions. Probably the pivotal missions that started was in the 1970s, and I would encourage everybody to look at the Viking models that are out there. Awesome piece of machinery. We learned a lot from those two Viking missions and those two Viking landers, and there were orbiters as well. There's a number of missions on the surface. I'm going to talk about the orbiters again here in a little bit, and so is Marcello. So I'm going to move to the landers for a second. So the Vikings, as I mentioned, and you can see those here, Pathfinder in the late 90s really kind of started our current era of missions on the surface. That technique for getting to the ground, which I'll talk about again here in just a few minutes, has been very successful. It's gotten both of the Opportunity missions, both Opportunity and Spirit to the ground, and it's also going to get the Mars Science Laboratory rover called...
Running and playing in the museum, especially on the escalators, is prohibited.
Yeah, that must have been meant for me, I guess. No playing in the museum. Okay, darn. So we have a number of those missions, and the landing site for Curiosity hasn't quite been chosen yet, and I think you might hear about that in a little bit, so I won't go into that from the next panel. So if we'll go to the next slide, please. I apologize for the lack of years on this at the top, but going from left to right, you'll see the Curiosity rover is our 2011 mission. We'll launch at the end of this calendar year. The day after Thanksgiving, actually, is the beginning of the window. And Mars is interesting because to get to Mars, Earth and Mars line up the best every 26 months. So we can't go, well, we can go every year, but it's most efficient from a fuel perspective and from a transit time perspective of every 26 months. So in 2013, we'll send a mission called MAVEN, which is an aeronomy mission. You've heard about Mars being wetter and warmer in the past, and now colder and drier. Part of that is a loss of atmosphere, and we don't exactly understand what happened and why it happened and the rate at which that happens. And so that mission is going to try to help us understand that. In 2016, and then in 2018, we're going to start working jointly with the European Space Agency, as I mentioned before, which is a perfect segue to Marcello. So now that he's all mic'd up, I'd like to introduce Marcello Corradini. He's from the European Space Agency, and he is our ESA program coordinator based at the Jet Propulsion Laboratory. So thanks for coming. Shall we sit down? Yeah. Okay. So Marcello actually is going to talk more about the 16 and the 18 missions here in just a little bit.
But also a little bit of history, because we heard so much about the water. But I want to take you by the hand in the last 40 years of exploration of Mars, comparing a little bit the evolution of the satellites and the evolution of the understanding of the planet. And everything started basically at the end of the 60s, beginning of the 70s. You were, you know, still in the sky, and your parents were not even thinking about you at that time. And the vision that we had at that time of planet Mars was, after all, rudimental, as it was rudimental the technology we had here on Earth. For you, it's difficult to imagine a society without internet, without digital photography, without cell phones, without Facebook. Well, we survived in a time when we didn't have those kind of things. And still, we were able to send satellites to Mars. But the problem is that when we got there, because the technology was not as advanced as today, we had a kind of a biased view at the very beginning of the red planet. And it looked, with the first missions, very similar to the moon. Lots of craters, lots of dust, lots of deserts, and nothing else. So at the beginning, we were really a kind of, a little bit of a delusion because we heard so much in the 40s and the 50s. Still in the 60s, at the beginning, people were talking about, forests and rivers, cities and civilization on Mars. We get there with the first satellites, and we just see desert and nothing else. Maybe if we can have my slides, it would help a little bit my presentation.
I hate to say this, but I got a couple to go here before you get your slides up.
All right,
if you
so
don't mind.
you go ahead.
Oh, maybe not.
Maybe not.
Maybe
I don't
not.
know.
I was going to talk about orbiters for a second. Can we go back to my set, please?
No problem.
No problem.
Let's see if they can follow that. If we can follow the weather on Mars, maybe we can follow your presentation as well. Yes.
And if you can't, just go to Marcello's if that's easier. That's fine.
Let's see what happens. Oh, well, it's me.
Go for it.
Okay. So next one. So this is the title. Well, basically, I already introduced it. Well, this cartoon basically summarizes very simply how the understanding that we have of water on Mars evolved with time. So as I said, the first time we went there in the 70s, we had the idea that Mars was a kind of a desert. Obviously, even if you go to the Sahara Desert or the Mojave Desert, it looks very dry. But actually, if you go really searching for water, you find a little bit of humidity here and there. And so that was the impression we had on Mars. And then with time, the following missions, a second wave of missions in the 80s, we realized that Mars was not so dry. Actually, there was a little bit of meteorology, we saw clouds, etc. And eventually, 10 years after 10 years, our understanding of the presence of waters on Mars has evolved dramatically to the point that today we can even imagine that once on Mars there were almost oceans. Not as many oceans as much water as we have on this planet, on planet Earth, but at least enough water to have created rivers and lakes and maybe even oceans, small oceans or seas. Can I have the next slide, please? Okay, so this is what we saw in the 70s with the Mariner 9 that was already mentioned. That was a satellite that was designed when the technology here, we not even had color televisions on Earth, okay? Forget about flat screens, so that was a dream, that was science fiction. We had big, bulky televisions in black and white, bad sounds, and big cameras. And so we had to use that technology to go to Mars. And the result was that, yes, we discovered polar caps, but nothing else. And then, obviously, technology advanced very rapidly. And in the next slides, you may see that there was a gigantic step forward with the Viking missions, basically with the analysis of the data that continue into the 80s. So this was something which is still unprecedented. I guess you agree that today, if we are asked together, NASA and ESA, to do the Viking mission today, we would have a big problem in doing it again. So at that time, our colleagues of that time, probably they were kind of a better of us, I must say. It's a kind of embarrassing to say, but it was at the end of the 70s, two gigantic landers landed softly on Mars. And then they were supported by two big orbiters. And with these devices, what we understood on Mars completely changed. We even saw frost forming on the surface. We saw clouds. We saw fog forming in the canyons. So we understood that Mars, from a meteorological point of view, was a kind of very lively planet. It was not this big rock of sand and craters as we thought 10 years before. And then our understanding of Mars continued to evolve. In the next slide, this is Mars Global Surveyor. This is when really we started to see clear characteristics of water flowing on Mars. The big question is, now we all understand with this mission in the 90s that there was water flowing on Mars. But the big question, and still we are not able to answer this question, is when this water was flowing on Mars. Well, this is a real challenge. And with the advancement of technology, we had more missions. And in the 2000, we're getting close to our age in the next slide. So this is the time when even Europe woke up, and eventually we joined NASA and America in the exploration, and Russia a little bit. They have been not so lucky in going to Mars because they sent lots of spacecraft and they lost them all. So we were really afraid of making mistakes in Europe. We've been thinking and thinking and thinking about making missions to Mars, and eventually we did it. We launched it in 2003. And because now we understood at the time of launch of Mars Express, that is the first European mission to Mars, that water was an important thing, we decided to really design a spacecraft that could monitor what we call the water cycle of Mars. In other words, we wanted to go from the underground to the surface, to the atmosphere, and to what Mars loses continuously towards outer space, and try to understand where the water is coming from, where it goes, and how it disappears. And so this mission is really very focused in understanding the water cycle. But this is also the mission that for the first time measured methane in the atmosphere of Mars. It was a big debate, no, it's a mistake, it's an interpretation error, but eventually most of the scientific community agreed that Mars Express, with an instrument that is called PSF, discovered for the first time traces of methane on Mars. Does that imply, as Jack said before, that we have cows on Mars having problems with their digestion? I don't think so. Methane can be produced geologically with volcanoes and so on. But the question is, if we can find much more methane, does that discovery have an implication on possible life forms, maybe somewhere in the depth of Mars? We don't know. So that's why we have to go back to Mars. And this time, because the technology and the complexity of the mission is huge, we really need to do it together. I mean, NASA by itself, European Space Agency by itself, we don't have the capability of continuing a major effort of exploration on Mars. So we got to do it together on Mars, and we will do it together at least for the next 20 years. So in the next slide, that is funny because it tells us how when we start penetrating with these penetrating radars into the surface of Mars, we find out that probably there is a lot of water in the underground of Mars. So the little man now has become a scuba diver, but not on the surface of Mars, in the underground of Mars, okay? So there is where we want to go looking for water and maybe life forms. Why so deep? Because first of all, you need water, and secondly, you need to be protected against the radiation. If you are on the surface, everything gets sterilized and everything dies in a matter of minutes. So if we want to go looking for something that exists, extant life on Mars, we gotta go deep. And so with the next missions, we will try to do that. Next slide, please. Okay, we can skip that because anyhow that's to show how intense is the effort of exploration on Mars. And it will continue even more, we hope, with new budgets. That's the plan, at least, if the politicians allow us to have the budgets to go to Mars. But you never know. Next slide, please. Okay, and now this is in 2016, where really NASA and ESA will work together. We'll be at the same time in orbit and on the surface with two major rovers. And so we're going to search for methane in the atmosphere, and at the same time we'll be able to drill for a few meters into the ground of Mars, looking for possible life forms, or maybe looking for sources of methane. So this is a major mission. These two missions will be working together in the 2018-2019 timeframe. The orbiter will be launched in 2016, is under construction in this very moment, and the two rovers, MAX-C and ExoMars, will be launched in 2018 and will arrive to Mars 6 months later. And so this is a major step forward in the exploration of Mars, and maybe we will have answer to these fundamental questions: where the water comes from, is there any life together with the water, is life producing methane, or is just a geological process? But we cannot stop there. And after 2018, we have to continue the exploration on Mars, and we'll continue to do it together. In the next slide, you see what's going to happen after 2018. One major step is a mission where we'll be able to land on Mars, get a sample, half a pound of rocks, and bring them back to the surface of the Earth. Now, you hear often on televisions or on the press or everywhere on internet that we should send astronauts to Mars. For the time being, for us, NASA and ESA, it's a major challenge to go to Mars and return a pound of rocks. Imagine returning hundreds of kilograms of human flesh without killing that human flesh. So that's why I put the question mark. Who knows when we'll be able to send astronauts there, but anyhow, one day we will do it, and it will be a major effort, and maybe is your future work, working on space mission that will take astronauts to Mars. Thank you.
Thanks, Marcello. So I'm going to pick it back up and talk a little bit about the hardware that allows us to do all these things, to find all these discoveries, to understand these things, and how we get them there, what they can do for us. As I mentioned earlier, the Curiosity rover, otherwise known as the Mars Science Laboratory, which is the overall mission, the rover is called Curiosity, is going at the end of 2011. I'm going to talk mainly about that. It's an excellent example of hardware, and this is, as I said earlier at the introduction, there's a little bit of science, a little bit of engineering, a little bit of everything for folks. So this will be the engineering part. Let's go ahead. So this is what the rover looks like. This is a large rover. Steve mentioned that Spirit and Opportunity are about 300 pounds. This is nearly 2,000 pounds. This is the size of a small car. I'm going to show you some actual footage of it and some images of what goes into making something like this. It looks fairly simple on the outside, but it's actually a pretty impressive engineering feat. What I'd first like to do, however, is run a short movie and introduce you to a gentleman named Dave Gruhl. Dave is the head of the test team at JPL, which is where this is being built, and he's going to take you through a quick, about a minute and a half tour of the assembly process that's going on right now for the Curiosity rover. On your brochures, there's actually a website link, and you can go watch this happen real time on a thing called Curiosity Cam, which I encourage you to do after this. So if you'd roll the video, please.
Hi, my name is Dave Gruhl, and I lead the team responsible for assembling, testing, and launching the next rover to land on the surface of Mars, Curiosity. The team just recently installed the mobility system onto the sides of the rover. That's the wheels. There's 6 wheels, 3 on each side, that all have to be verified that their actuators work. And then there's steering actuators too, which is what we use to actually turn the rover when it's on the surface. There are 10 small little motors that make up that mobility system, and what the team is doing right now is they're going through and making sure that each of those wheels spins forward and backwards and rotates if necessary from a steering point of view, so that when the rover gets down to the surface of Mars, it can successfully navigate itself over the rocks and the terrain that are actually there on the surface. As soon as we finish up the mobility checkout, they'll be putting the mast on the top deck of the rover, and the mast is more cameras and imaging that allows us to take stereo pictures off in the distance of Mars. Just like your eyes work in a stereo pair, this camera will also return us stereo imagery from the surface of Mars. Once that's complete, then the front deck of the rover, which is empty right now, is where we'll put the robotic arm. The robotic arm is a device that reaches out 6 feet or so and actually touches the surface, takes samples, and then deposits those samples back into the innards of the rover for the science instruments to analyze and determine what the elemental compositions are of the surface of Mars. Over here on my left, you'll see the descent stage. The descent stage just went through a test where they actually shook it, just like it would experience when it's out going through the launch. And they wanted to make sure that the design held together and then nothing broke, and everything was successful with that test too. This has been your update on the assembly of the Curiosity vehicle. As you can see, Curiosity is looking more and more like a rover every day, and the team is working hard as we aim for our launch scheduled for November of 2011.
Okay, so if we can go to the next slide, please. So you saw a little bit of an animation of it. You've seen it from a distance. Now let's kind of get up close and personal with some of the hardware here on the Mars Science Laboratory. So this is what it looks like. You'll see that in that masthead, there's not only the eyes, but there's a thing called chemistry camera, which is really cool. I hope we can get sound effects from it. You'll actually see it in a little bit in another animation. But it's got a laser in it, so it stands off, and 20 feet away, it can zap that laser at a rock, create a plasma from that rock, and then analyze what's in that and decide whether it's worth driving over there to look at it. The main REMS is actually an instrument that provides meteorological data, wind speed, pressure, temperature, things like that. We had a question earlier about meteorology. We're going to measure it directly. Just like we had a question about radiation. There's an instrument on here called RAD that measures the radiation at the surface of the planet. So we will get our first really good solid data set for that. And then inside is really where the hardest working and the most complicated instruments are. And essentially we've taken a chemistry laboratory and we've squished it down into a couple of small boxes, stuck it inside this rover, and the arm is going to actually drill holes in rocks and move that material into those chemistry labs to understand what's in that. The whole idea is, you heard the word earlier, habitability. Big long word for, is this an area that could have been a habitat or is it a habitat? That's the key. MSL is the scientific transition mission from understanding the water cycles on the planet to understanding if things could or could have survived on the planet. Next slide, please. To get to the surface, though, it has an atmosphere. Some of you remember, many of you remember the Apollo programs. Everybody remembers the shuttle program because we're still doing it. That you have an atmosphere you have to get through. Mars has an atmosphere we have to get through. So getting things from the top of that atmosphere to the surface safely is a big challenge. And as Marcello had mentioned, many of us have tried, and the U.S. hasn't been successful every time either. The success rate for everybody on the Earth trying to get to the surface is in the 60 to 70% category. So it's really a tough thing to do. Just enough atmosphere, you have to worry about it. Not enough atmosphere to help you, like here on Earth where it's nice and thick and you can slow down easily. These are the pieces. The thing on the top is the cruise stage. That keeps the spacecraft and everything alive, provides power and other support systems on the way to Mars, which is about an 8-month journey. The top white thing, just below the cruise stage, and then the dark thing at the bottom are the aeroshell. So just like the old Apollo capsules, the rover is encased, just like the astronauts were, in this device. And that dark brown thing, that heat shield, takes all the heat on the entry through the Mars atmosphere. The next thing down, looks kind of like a spider, is called a sky crane, or otherwise known as the descent stage. You saw it in Dave's picture or his video a minute ago. That actually is essentially a rocket-powered helicopter, and that's going to land the rover. And then the rover, which doesn't look much like a rover in this, is the next thing down. It's all folded up to be able to fit into this clamshell. I'm going to show you a video at the end of how all this stuff unpacks and walk you through it as we get to the surface, which is, in my opinion, probably one of the greatest engineering feats that's ever been actually invented. It's absolutely unbelievable when you see it. So next slide, please. I told you it was big. That's a Mini Cooper, and that's the back shell that I showed you. It was white in the previous picture, so you can see how big this is. As a matter of fact, the Apollo capsule, and there's one of those on the floor you should go look at, easily fits inside this, and you can close it up. You could probably put 6 or 7 astronauts in this thing, but we couldn't get them back, so they probably don't want to go. Next one, please. This is the inside of the rover. So the rover looks nice, got 6 sides, excuse me. You know, looks like a nice box. There's a lot of stuff inside this. These are what we call the avionics. So these boxes are the brains of the thing. The computers are in there. The power control systems are in there. Because of the temperatures at Mars that you heard from Jack and Steve about, there's heating control systems in there. There's batteries in there. And then this has a small nuclear generator on it that creates heat, and we use that for both heat and energy. And the control electronics for that are in there. That big empty cavern in the top right is actually where one of those chemistry laboratory instruments goes. I'm going to show you that next. Next slide, please. This is 2 pictures from 2 different angles of the same instrument called sample analysis at Mars. For the students who've had chemistry lab, those are essentially a whole ring of test tubes there, and we have the ability to sample over 70 individual samples on the surface of Mars. So we're going to have a drill, and we're going to drill holes, we're going to process that material, and it's going to come back and go through all these different chemistry steps in this device. This is an amazingly complicated thing. This usually will be a couple of stand-up racks in a chemistry laboratory, but we've crammed it down into this little box that's about this big inside MSL, Curiosity rover. Next slide, please. And this is what's going to do the drilling. This is a complicated looking device because it actually is. On the right end, you'll see 2 fingers sticking out. In between those is the drill itself. On the other side, I'm sorry you can't see it, is actually the processing system that will sieve will sieve the material and route it around and get it into the rover body itself. The red box that's facing you is actually a device to take clean dust and things off of rocks so that you don't sample the surface dust. You actually are able to sample the rock itself. And then just behind it, there's a little black box with a big silver colored cable that goes into it. That's a microscope. We call it a hand lens imager. And so that's another tool that we'll use. This weighs about 100 pounds, and it's at the end of a 6-foot arm. So it's quite a piece of engineering to make this guy work. Next one, please. This is actually the descent stage, or the sky crane, with the rover wrapped up and packed up underneath it. You can see one wheel in it, but I want to show you that because I think the next slide is we're going to go into an animation. I'm sorry, we have one more slide. Next one, please. This is the whole thing put together. I showed you the cartoon of it broken apart. This is what we call the stack. Every once in a while, to make sure everything works together, we put it all together and test it as a single unit, and that's the stack. If you look at the bottom, you can see little guys down there in their bunny suits, as we call them, walking around, so it gives you an idea how big this is. So the next thing I'm going to show you is an animation. And this animation is actually beginning at the top of the atmosphere, and this is how we get the Curiosity rover unpacked and to the ground. This whole thing is called the 6 minutes of terror. I have yet to learn how to hold my breath for 6 minutes. I'm working on it. I tried it on Phoenix when we did that in 2008, and I turned blue and it didn't work well. So we're going to give it another try here, but this is an amazing sequence. I'm going to walk you through it. So we start at the top of the atmosphere at about 12,000 miles an hour. As it comes through about the atmosphere, the heat shield takes up about 95% of the energy of getting to the ground. When we are around supersonic, a parachute comes out. This takes out about 4% of the remaining 5%. Heat shield comes off, the rover wheels come down, wait for it, it comes out of the back shell, okay? So the sky crane and the rover are attached to each other. So this is a rocket-powered helicopter now on the way to the ground. Horizontally, it's barely moving. Vertically, it's a meter or so a second. And now it's going to roll the rover down on a set of cables from the sky crane. It's now going to slowly descend. It's going to touch down. When it recognizes touchdown, and the rover is the one to tell itself that it's on the ground, it'll cut the cables. Sky crane goes away and just crashes off in the distance. Don't need it anymore. Its job is done. Out of fuel, basically. Now we unpack the rover. So that sequence that you just saw in about 40 seconds is 6 minutes long. So it's because the light time, the radio time between Mars and Earth is around 7 minutes or 8 minutes. This whole thing happens before we even see it start. So we don't know the end until it's all over. So I'm going to let this run for another minute or so. You will see it drive off. You can keep an eye on this. It's going to actually show you how ChemCam is going to work, which is kind of fun. But this is the end of the presentations, and I'm going to open it up for questions. We got enough time for just a couple of questions. I think you were first.
If I look at the mass of the rover, what fraction of the rover mass, what fraction is the rover mass of the entire package?
The entry mass at the top of the atmosphere is a little over 3,000 kilograms. And the landed mass, which is the rover and all the instruments, is around 970 kilograms. So it's about a 3-to-1 ratio.
If you were to do aeronomy on the surface of Mars in this future exploration, have you considered the use of UAV-style devices to help you sample different layers of the atmosphere? Is that part of the planning? Is that been considered?
Many things have been looked at, and I'll let you answer part of this. Yeah. But I mean, we've looked at balloons, and we've looked at Mars airplanes and things like that. They're difficult to inflate because there's not enough air for propellers and jet engines and things like that. You know, you're rocket powered, so your lifetime is short. And so there's issues with doing that. And you also only cover a very small area by flying through it if you had an airplane, or you can't control it because a balloon just drifts. So right now, it seems like spaceborne, satellite-based seems to be more efficient. You want to add to that?
I can confirm that. Maybe in a future effort of exploration, some terrestrial technique could be used. For instance, having at the same time a satellite and a lidar on the surface of Mars, pointing with a laser towards the sky, and so you have a double probing top-down and bottom-up in order to study all possible composition and turbulence and wind speed and wind fields, etc. For the time being, we have to be content with the very sophisticated orbiters that, with new technologies, new spectrometers can provide us with a lot of information on composition and dynamics of the atmosphere of Mars.
Thanks, Mark.
One more quick thought.
Really quick, because I'm
Really
running out of
quick.
time.
Mars sample return. Are you considering the use of in situ resources to throw your samples back to save you a lot of mass?
The question was whether we're looking to use in situ resources, in other words, make things there, fuel and other things. And right now the answer is we don't think we have to do that to be able to execute that mission. So, next question, please.
Yes. I'm curious about the delay from ground control on Earth. Whenever you're creating a sequence of like operations for the rover, you expect like how long of a delay? I'm curious.
Mm-hmm. Do you want me to talk about you? Okay. So let's take rovers. I think you mentioned rovers as an example. So typically what we do is you build a command load of software commands, things you want the rover to do, and then you upload those to the rover. The rover will not execute those in real time. You typically load them on, make sure that all the things loaded properly, and then execute those commands at a different time. Then next, because you're not always in contact with it. Now we do use the orbiters for most of the communications relay, but we don't see them all the time because both planets are rotating. So then it goes off and it does the execution, and then when you talk to it the next time, you'll get the data set back. So we don't try to do things telerobotically because that light time is the problem, right?
So it's basically a sequence of programs and things like that that carry out the different operations.
That's right, that's right. And to make things efficient, the smarter the rover can be, such as understanding what's a hazard, what it can and cannot drive over, and we have those smarts now on Spirit and Opportunity. We didn't before. You can actually do more because the rover itself is smarter. So that's how we improve things. Thank you. Yes, sir.
What? I can't do it.
Yes,
no.
Okay.
Yeah.
We don't bite.
No, we don't.
Can I just, yeah.
Now, I hope we can answer your question. That's going to be the hard part.
That's right.
What's going to be the difference between the Curiosity and the ones that are up there now?
Oh, that's a great question. The ones that are up there now have very limited payloads. It has very few science instruments. It has a camera and a couple of instruments for looking at minerals. So it doesn't have this chemistry laboratory. That's the big deal about Mars Science Lab and Curiosity, is it is a laboratory. It's a chemistry laboratory on the surface of Mars. It's a good question.
Yeah,
nice.
absolutely.
You got a follow-up?
Well, the other question was, so what's the difference in speed as far as will Curiosity cover more ground in a shorter period of time?
That's also a good question. They actually drive at about the same speed. MSL Curiosity is not really any faster, but it's designed to drive farther. So as you heard from Steve Squires, Spirit and Opportunity were only designed, we only planned them going about 600 meters. Curiosity is designed to do 20 kilometers. So it's designed to live a couple of years and drive 20 kilometers, which is 10 miles. Okay, thank you very much, Marcello. Thank you.
Thank you, Beth.
So the next panel is on where we're going scientifically in the future, what we think we might find, and our future aspirations and expectations and hopes. To lead that panel, I'd like to introduce Michael Meyer, who's the Chief Scientist for the Mars program at NASA headquarters. Michael?
Thanks, Mark.
Good to see you. Thanks.
Now we're in the third part of the program, and we're going to move from following the water toward the idea of looking for signs of life. And basically, it was back in about 1995 that we recognized that looking for life on another planet is an extremely difficult and challenging problem. So he commissioned a report, and it was published, basically an exobiology strategy for exploring Mars. And what it did, it recommended a series of missions where you start with orbital reconnaissance, you send rovers to the planet to confirm what you thought you saw from orbit and also do some exploration on their own. And you iterate this several times as you improve your knowledge about the planet, because you can't understand the possibility of life unless you understand the planetary context. So you have to know the planet before you can reasonably ask the question of whether or not it is ever possible to have life there and where you might look for it. So with that, you do orbital reconnaissance, you go to the surface and explore, confirm what you thought you learned from orbit, study in detail, and then eventually, one of the things that we would like to do is do sample return so we can put our best instruments here on Earth on that thing to understand whether or not a particular planet has evolved life. So with that understanding and that strategy laid out over 15 years ago, we have been following that. And a good portion of that strategy is encompassed in the idea of follow the water. And you know what? We can check that box. We found water. We found it in several different places. We now have an understanding where water was on the planet, not only in place, but to some degree in time. Now comes the challenging part. If their water was there, did that actually create an environment that's amenable to life? And if that environment really did exist, did life actually start and evolve there? So with that, we're going to start the third panel. And what I want to do, we have assembled 3 experts that cover a wide range of expertise that are going to tell us about astrobiology approaches, a kind of a how do you look for life, talk about places on Mars that we think had water on the surface, and it may be places that are potentially amenable to life, and then also part of the approach of how we explore the planet. So first up, I want to introduce Mary Wojtek. She's the head of the astrobiology program at NASA. And, okay, I'll stand over here. And her background, she comes from the U.S. Geological Survey, but she's a microbial ecologist and a biochemist, and she's been looking at life in a couple of different ranges and studying things anywhere from potable water to life in extreme environments to the deep biosphere. Our next panelist is John Grant, who you've heard about before, and he's the chair of the Center of Earth and Planetary Studies here at the Air and Space Museum. He's also been, as you heard, very much involved in the rover exploration on Mars now, but the more important part of why he's here is that he's been leading the scientific community effort to find scientifically the most promising places on Mars and where we should go and whether or not it would be safe. So a very important aspect of where to go on the planet. And then the third panelist we have is Jen Eigenbrode. She's a biogeochemist and at Goddard Space Flight Center. And she has been interested in helping with the development of some of the instruments we're going to Mars, particularly SAM. And she's been looking for the signs of life here on ancient Earth and how to apply that approach to when we go to other planets such as Mars. So with that, what I'd like to do is start the panel off with Mary Wojtek to tell us about astrobiology and an approach for looking for life elsewhere.
Thank you, Mike. May I have my first slide? So astrobiology at NASA and as a scientific discipline is the study of the origin and evolution of life on this planet in order to understand what controls the distribution of life here on Earth as well as other places in our solar system and beyond. The study includes research that's near and dear to my heart, which is looking at the limits to life, where organisms can grow, what they require to grow, finding out that what we consider habitable and the temperatures, for example, that we keep our homes at is not at all what organisms can withstand. They can grow in very cold temperatures, minus 20 degrees C. They can grow at very warm temperatures above the temperature that water will boil. They can grow in acid environments, in base environments, very dry environments. It's really remarkable. With and without oxygen, where they can grow and thrive. And so astrobiology looks at what defines those limits so that we can actually define how an environment could support life and what would make it habitable. We've been talking a lot about habitability here. Now, the field of study has really been informing NASA's program to search for signs of life, both because it studies this information about Earth organisms and because it spends a lot of time looking at other alternative environments or the environments of alternative bodies in our solar system. So that combination of information allows us to answer some fundamental questions of where did we come from on this planet, and are we alone? Is there life elsewhere? So I'm gonna have the next slide. So some of the fundamental things that we know about life, or life as we know it, is number one, it needs water. And that has certainly been the mantra for NASA's, a lot of NASA's and other agencies' explorations of the solar system, looking for that water. And we've discovered not only on Mars is there quite a bit of water, nearly everywhere we look it seems these days, but also that water is very common throughout the solar system and beyond. We find ices many places. In addition to that, we know that all life on Earth is made up of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are elements that make up all the components that go into the molecules or the building blocks of life. And we also find those elements as well as some of those very building blocks distributed throughout the solar system and beyond. In addition, life needs to build a cell. It needs to define itself. And the picture on the upper right on my figure there is actually a fossil cell. And so we know that cells need to define again itself from its environment in order to do the business to grow, reproduce, and do its metabolism. In addition, in the lower left, there's a representation of cells. All life on Earth needs energy. And that energy can come from a variety of sources. It often leaves a signature behind that's based on its ability to exploit gradients in chemistry, gradients in energy itself. And that's something that's critical, a critical component of all life as we know it. And then the final thing I'll just mention is that we've come to discover or firmly believe that all life on Earth requires a two-component system that involves nucleic acids like DNA and RNA that can store the basic blueprint for life. That's all the information a cell needs to do all of its business. And that there's a mechanism to convert that information, well, to reproduce it, convert that information into things like proteins that actually carry out all of that activity that it needs to do to maintain itself and to grow and thrive. And that these particular molecules, or this system as a whole, is able to respond to Darwinian evolution. So that allows, on this planet, has allowed the great diversification that we see of life on this planet, from things as small as single-cell bacteria, all the way up to ourselves and a wide variety of eukaryotes, which are the multicellular animals or and plants, and that I'm sure all of you have learned about in school. So one of the challenges in looking for life elsewhere is, first of all, I've just talked to you about what we know about life here. And as many people have said, our search is based on what we know, because that's the information that we have. Our laboratory has been the Earth. That's what we know. How do you expand what we know about life here on Earth to be more generalized so that we can think about life as we don't know it? And so I'm just going to do a little ad here for a study that was done by the National Academy of Sciences, and it's called The Limits of Organic Life in Planetary Systems. It's been nicknamed the Weird Life book. And basically, we had a number of preeminent scientists get together and discuss what are other possibilities. Can we use something else besides water? Can things grow in other solvents? We saw that there's lakes of methane on Titan, which is one of the bodies that we're interested in. Could life grow in a solvent like a liquid methane? They also considered other sorts of chemistry, the replacement of those basic building blocks that I mentioned earlier, other types of energy. And so scientists are really trying to expand it to make the search for life in other places as broad as possible. The worst thing in the world would be for us to go somewhere, have such a narrow definition of what we were looking for and instruments that would measure that we could completely miss something that would later, or if it were here and we found it, we might consider to be life. So it's very important that we keep our search broad. All of these things that I've mentioned in terms of life as we know it, we have been considering how do we then look for it if it's not present now but might be in the past, and how are we going to distinguish it from other sources that might have formed those features. We tend to call some of these things biosignatures. A fossil is a biosignature. It's a remnant of an evidence of life having been there, and my colleague Jen is going to talk a little bit more about that. And that's one of the challenges, because there are many things that might look like a fossil. There are many kind of organic compounds that are found in cells, but that are also made other ways. And so this is going to be part of the challenge as well. So you may hear a little bit more about biosignatures. I thought I'd introduce it to you so you can think about that. Think about how you might abstract this for the search. I think in addition to what we know about life on Earth too, and this concept of habitability, I'm going to turn this over very quickly to John, who's going to talk to you about how we consider looking for targets. What do we need to know about the places that we're going that match to what we understand about habitability in order to make it something that we might select or something we can predict would provide useful information? And with that, it's your turn.
Thank you very much, Mary.
Too much?
I'm going to talk to you a little bit about one of the first steps along the way towards seeking signs of life on Mars, and that is, where do you go to understand the range and potential habitability of the planet? And if I could get the first graphic up, I'll tell you a little bit about how we're going about doing that. As you've heard from some of the speakers here earlier, there's been discoveries of a lot of water and a lot of different inventories on Mars. And we've also understood that it's a complex world. I mean, there's a lot of territory to cover. So where do you put down this Curiosity rover to get the biggest bang for your buck? Well, this graphic basically shows you a map of Mars, but it's been changed from what you saw from what Jack Mustard showed you. What you see here is a map where everything that is above an elevation of 0 kilometers, which you can sort of think of in this regard, although it's not, a sort of sea level, a datum, if you will, that we can't land above, because if we do, we don't have all of the time and space, literally, that we need to complete the steps that Doug McQuitchen described in terms of landing the Curiosity rover. In addition, there's places that are too far north and too far south, and that's masked out by the white areas that you see in this graphic. So we're sort of limited here, as you see, to a band, but a very wide band, between 30 north and 30 south on the planet of the surface. And fortunately, that covers an incredible diversity of potential landing sites. How do we do this? Well, I wouldn't pretend for a second to know enough about our planet, much less Mars, to be able to say, this is the place you ought to go. The way you do that is you bring in a variety of expertise. You bring in the people that are involved in the mission. You bring in people in the scientific community that are involved in the analysis of the data that's been collected by all the missions that have been described here today. And what we've done through that process is identify a whole range of candidate landing sites. Those are shown by these red dots, the red dots that you see in this graphic. And they range from the floor of Valles Marineris, this huge canyon system that John Mustard described, to areas that are very much right next door to where the Opportunity rover that Steve Squires talked about is today. The places that we've converged upon for the final 4, if you will, we haven't picked the final landing site yet, but will later this year, are shown in blue. And what I'd like to do for just a second is give you an outline of how those 4 sites are perceived to fit into the template that Mary has outlined for you about habitability and the goals of the Curiosity rover. So could I have the next graphic, please? So what you see in this graphic on the left-hand side is a zoom-in view of places on Mars corresponding to those 4 blue circles you saw in the previous slide. And what you see in the colors here is the elevation, the topography. Blue is low, red is high, green is somewhere in the middle. And so the landing sites shown in those sort of oval or ellipse-shaped white lines are basically within impact craters in all but one example. The 4 final candidate sites are from top to bottom: Eberswalde crater, Gale crater, Holden crater, and Marth, Valles. What we're looking at in these various locations, starting with Eberswalde crater on the top, are examples of places where habitability can be evaluated. And to do that, a record of past conditions is likely to be preserved. So with Eberswalde crater, shown in the yellow box to the left and then blown up in the middle, is an area where it appears that a river flowed into this crater, creating a lake and depositing sediments in a delta, much like you would see in a larger version in the Mississippi River Delta here on Earth. Those sediments preserve and record the depositional conditions and processes. And if Curiosity can go there and evaluate those, we can say something perhaps about habitability on Mars. Now, we would land away from this delta in an area further out on the crater floor, which is shown to the top right, where we see evidence of past rivers that have drained down into this crater before it filled with water with the delta. You heard John Mustard talk a little bit about Gale Crater. The reason for going here is this incredibly thick sequence of materials, 5 kilometers thick, that record that transition from earlier sort of neutral conditions where clays were forming to more acidic, dry conditions. At Holden Crater, which is the third one down from the left, it's a very large crater, about 150 kilometers in diameter, and what we've got there is a sequence of alluvial fans, much like you might see along the sides of Death Valley or other valleys out in the southwestern United States, and we would land on those as shown to the third one down on the right. However, the ultimate goal of our exploration here is shown in the third down in the middle, and that is these finely layered sediments that we see on the floor of Holden that probably were deposited in a lake, a standing body of water, or in a very distal portion of those alluvial fans. And those fans, much like the Delta and Eberswalde, would record this sequence, this history of depositional activity and the habitability that may have occurred there. And then finally, Marth Vallis, shown on the bottom left, is an area that's up north of all of the other three that I've described, and it straddles a very ancient sequence of stratigraphy, layers on Mars, that were deposited in this very early history that John Mustard described. Clays are widespread here, and there's a very definite sequence in which they're layered. And those layers will tell us something about the conditions responsible for their formation, and again, in turn, about the habitability that may, potential that those layers may have recorded. We would basically land on those layers, and so what you see in the bottom middle and bottom right are examples of how that stratigraphy varies from location to location. By exploring those differences and by understanding them, we can tell something about how conditions might have changed over time. So that's sort of a thumbnail sketch, if we can go to the last graphic here, of where we would be going with Curiosity. But you heard Doug and Marcello describe future missions. And we're using our orbital assets that we have now to look ahead. There's a variety of places on Mars that are being imaged as we speak to be considered as future landing sites. There's interpretation of what the features are that tell us something about their merits for future sample return, for example. Those could include possible spring deposits shown in the northern plains by the box on the left. Putative chloride deposits, which may represent this sort of drying up lakes or drying up bodies of water, similar to what Jack described earlier. Or finally, in transitions over here, in an area known as Northeast Syrtis, we see an incredible diversity of mineralogy that says something about how water has interacted with the rocks over time. And when it occurred was across this boundary from wet and more neutral to dry or more acidic. And with that, I'll turn it over to Jen Eigenbrode to tell us something a little bit about the Curiosity mission.
Okay. You can pull up my slides then. Well, the Mars Science Laboratory, the rover's Curiosity, it's called a laboratory for a reason. It has a full set of instruments on board that can tell us all about the rocks that we're going to encounter with that rover. Now, if you pull up the first slide, please. One of the key questions that we are looking for, one of the key questions we're asking is, where are the organic molecules? Now, why would we search for organic molecules on Mars? We're seeking signs of life on a planet that's very close to home, and that at one point during the evolution of the solar system, we think that it might have been habitable in terms of being close enough to the sun to receive enough energy to be warm enough for life to exist there. Okay, the atmosphere was very different, and there was probably water on Mars. We've already covered that a lot with some of the other presentations. Now, organic molecules can be both nutrients for organisms, but they can also be parts of the organisms. They might be waste products of organisms. In either way, organic molecules are a fundamental part of understanding whether or not the environments that we look at in Mars might have been habitable, meaning they either supported life or they could have supported life. Next slide, please. Now, on Earth, we find organic molecules throughout the geological rock record.
Here's an example of a rock that is billions of years old. And in this, we find evidence of microorganisms. And we find that evidence in terms of both the organic molecules that are present, but also in terms of the package of chemistry and features that we see in the rocks. Some of those features might even be things that look like microorganisms, things that you might find under a microscope. Next slide, please. Here's an example of how we would find such a molecule. Take an example of a polar bear. We're all familiar with polar bears. They live in the Arctic. You don't want to encounter one at close range. When it dies, it's going to leave behind a fossil skeleton. And we might find that fossil skeleton in the rock record. Well, in a similar way, microorganisms have all sorts of organic molecules that make up their cells. And some of those in particular would be lipids that make up the membrane. The membrane is the outer portion of the cell, or it makes up the walls of the nucleus and other organelles inside the cell. Those lipids are complex molecules. They have carbon-carbon bonds, and in this image that I'm showing you, every line represents a carbon-carbon bond. Okay, so this is a big molecule, and it has all sorts of oxygens hanging off of it. It might have phosphorus, it might have sulfur, nitrogens. It can be kind of complex. Well, that molecule will get put into the rock record when the microorganism dies. And under certain conditions, that carbon-carbon structure can get preserved, even for billions of years. And we can uncover that type of molecule, and we call that a molecular fossil. So when we go to Mars with Curiosity, we're taking with us an instrument that can actually look for organic molecules. It is capable of detecting a fossil, a molecular fossil that we might anticipate from an organism as small as a microorganism. And we're going to look for those, so next slide. And we're going to look for those in the ancient rock record. Now this is an image, it's an artist's rendition of the Meridiani area, and it shows water in the crater there. This was taken from a website called Space for Case, so you can find it on the web at www.spaceforcase.com. And what's interesting about it is that it kind of presents this idea, this creative conception of what it might have been like millions of years ago on Mars. And these are the types of environments. Here, a crater filled with water, places where all of the other elements of habitability are essential. Source of water, possible sources of energy, maybe organic molecules. These are the things that we're looking for. This is what makes up a habitable place. And we're looking for the rock record that represents an environment like this. These are the types of places that we might actually succeed in finding organic molecules. And this is what John was talking about with the different landing sites. All of them kind of fulfill this niche. What we're hoping to do is find those organic molecules. Next slide. And those organic molecules could tell us a variety of things. One is they can tell us about different sources. Those sources might be meteorite sources. They could be geological. The actual processes that happen by a planet can produce organic molecules. And perhaps they're coming from life. We don't know yet. So we have 3 categories of sources. But then on top of that, all those organic molecules go through other types of processes. And sometimes they keep a record of those processes. They might tell you about surface processes, things that have happened since they were originally formed. We're going to try and unresolve what those molecules actually say if we find them. This is an image here of the Mars Science Laboratory rover Curiosity. And it's actually, you can see the beam of the laser beam pointing off of it. That's the ChemCam instrument zapping a rock. And what it's going to do is it's going to look, it's a tool that we're using to survey the types of elements that are in those rocks. We're going to be looking for variations in those elements. We're also going to be looking at features of the rocks. They can tell us different things about the energy of the environment that formed the rocks in the first place. They can tell us all sorts of things about what the chemistry of that environment was like, what to have expected. Was it a lake? Was it a delta? Was it a river channel? We don't know, but we'll be able to figure those types of things out. All of that information becomes the context for understanding the other features that we see, which could include organic molecules. We need to have that full package of information in order to address the questions of habitability. To actually seek signs of life requires more than just organic molecules. It requires a whole package of chemistry and morphologies and structures of the rocks. We're going to be able to do that. So after zapping the rocks with the chem laser and taking pictures and everything, we'll go up to a rock, we can drill it, and we can put that into the SAM instrument, which is in the belly of the rover, and that instrument allows us to look for organic molecules. It has what's called a gas chromatograph mass spectrometer. And we'll be able to separate out the different molecules and see what's there. The discovery of an organic molecule on Mars will be a big deal. Right now, we don't have any evidence of organic molecules on Mars itself. There is suggestions from meteorites that maybe organic molecules are there. So finding an organic molecule all on its own is a big discovery. If we don't find organic molecules on Mars, it's not a full loss. If you think about every single Mars mission that we have had, every single one has completely changed our perspective of the red planet. We have always discovered something, and this time around we're going with a whole laboratory of instruments. We're going to be looking at these rocks in a way we've never been able to look at them before, and because of that we're going to be discovering new things. And all of those ideas that have been presented about what we think happened on Mars, they're going to change. They're going to evolve into something new, and nobody can predict what that is yet. But our perception of Mars will change, and we are going to have some discoveries.
Thank you very much. We have time for a few questions, and while we're waiting for people to come up, the word of the day is alluvial. John?
Sorry about that, a little jargon there for you. Alluvial is a deposit that's created by a river flowing down and dumping its sediment as it does. And in the form that I used it, that's in a sort of dry setting like you'd see out in the mountainous Southwest, where a thunderstorm erodes the sediment, it flashes down out of the mountains and is deposited in a fan near the base of those mountains.
Great. Thanks, John. Question?
Of the 4 possible landing sites for Curiosity, are there any that people are particularly leaning towards, or is it pretty much an even bet for all 4?
I'm sorry, I missed part of the question.
Of the 4 possible landing sites for Curiosity, are there any that people are particularly leaning towards, or is it fairly even for all 4?
Is there a preferred landing site?
If you ask 4 different people, you will get 4 different answers. We have had a very, very structured but vigorous discussion about the merits of each site. And one thing that everyone agrees on is that any of the 4, were it to be picked for Curiosity, would be an excellent landing site. We all have different sort of sense of expertise and our own favorites, but what we need to factor in, and is going on now, is a sense of how each of those sites allows Curiosity to get done what it needs to. And once we sort of feed that into the mix, I suspect that the science coupled with what Curiosity can do is going to lead to a favorite. And that's going to allow us to pick.
Do you have any personal favorites?
He's not allowed to say that because he's leading the scientific community search for which site we're going to go to. So. Yes.
I can't remember which mission was on, but I was fascinated by the aspect of perhaps trying to determine microorganism life by looking at respiration type experiments where you're actually either putting in a label, a carbon-14 label, and seeing if you're getting evolution of labeled carbon dioxide. First question is are experiments like that being considered in this or future missions to try to, as one handle of determining microorganism content?
Yeah, please.
The mission that you're referring to is the Viking mission. Yep, it was Viking. And my understanding is that there haven't been many considerations for pursuing more of those types of experiments on Mars. And part of the reason for that is that the results from the first one were very controversial, and it clearly showed that there were a lot of unknowns about the chemistry of the rocks and the sediments on the surface of Mars, and without having a better grasp of what that chemistry was, it always kind of throws some questions into the mix of what the results really mean.
Whether it's an abiotic or a biotic.
That's right, that's right. And so we really need to have a better grasp of what the chemistry of the rocks and sediments is like on Mars first.
Okay, my last question also, just comment on...
Let Mary add to that.
I was going to add something else, that a lot of the life detection experiments that people have talked about, again, are Terran specific. And I think if nothing else in the last decade or so, or certainly since the time of those original experiments, we have learned so much about the possibilities of life and what they can actually do and what you would be looking for. So I think, again, we need to be very careful about being too specific with an analysis, and some think that a life detection experiment would require more knowledge about our target than we actually currently have, so knowing more about Mars than we really know now. And also, it would be tailored too much towards an experiment that says, is there an organism that I find in my backyard up on Mars, because we know how it behaves. And so, again, it's a little risky at this point.
The only other question also is just to give us a comment or two on the possibility of eventually investigating or looking for DNA or RNA in any of these samples as a marker of life. Is that being considered?
Well, we can both say. Looking at them specifically as in an analysis for DNA only or specifically is not considered for MSL, and it's not necessarily planned for the future. However, Jen can speak to the fact that if DNA is there, the instrument that she's involved in will see it.
Well, it will not see DNA as a molecule all on its own. It will see components that might make up the DNA. Yeah.
So evidence.
And you actually might send an experiment that could measure DNA as a check to make sure you're not sending terrestrial microorganisms. But.
Okay. I guess for any and all of the panelists, there was this little alleged microbe in the meteorite. Okay. What are your collected or individual opinions as to why this little thing was not the first data point for astrobiology?
So the question that I had was related to a meteorite called ALH 84001 that purported evidence of life because it came from Mars, and there are 5 interesting aspects to it. Essentially, the conclusion from that meteorite is there's not enough information in that meteorite to conclude whether or not it is evidence of life. So it depends on which researcher you talk to, whether or not it is evidence of life or just interesting or chemistry that mimics signs of life.
What are the weakest arguments in your minds?
Essentially, one of the important findings is reduced carbon in the meteorite. The problem is it's hard to tell where it came from. And so that's probably the real crux of the matter. And part of the issue is that we can come up with physical chemical processes that will produce similar reduced carbon here on Earth, and whether or not that process actually, that rock experienced that process, is one of the things we don't know. We don't have a context for where that rock came from. And one of the real advantages of MSL is you go to the place, you'll know the context because you're studying a region. So when you pick up something that's interesting, you'll know what its environment is. And Jen, you might want to add something.
Yeah, so imagine you have a rock that gets blasted off of Mars. It travels through space. Who knows what's happening to it when it's traveling through space? It's certainly going to be bombarded by a lot of cosmic radiation. Then it has to pass through the Earth atmosphere. It probably breaks up to some degree, gets heated up a lot, and then it's going to land someplace. And in this case, it landed in the ice of Antarctica. Once it's in the ice, it's going to sit there for a while. Who knows how long? It's processing, it's processing. There are things that happen inside ice. There are chemical reactions that can happen. And if there are microorganisms around in the ice, and they see a rock nearby and it's got nutrients and food and all sorts of other interesting things that it wants, those can actually come in and make that their home. Those are all possibilities, and we can't constrain any of those. The best that we can do is try and find features, the features of the meteorite in analog materials of Earth, and try and understand all of the processes that might contribute to those features, and then ask the question, could those features have happened on Earth or on Mars, or maybe both? And so really, it's not constrained well enough.
Thank you.
Last question?
Well, if the media, the Post, is to be believed, within the last couple of months they found evidence of a non-carbon-based life form on this planet. And so my question is, how does that affect the experiments that you all do on Mars?
So I'll take that. Number one, the finding wasn't a replacement of carbon. That organism absolutely is carbon-based. The finding was they found an organism isolated from Mono Lake, which is an extreme environment. It has a very high pH. It's got lots of metals around, and it has a lot of phosphate as well. But this particular organism appears to be able to grow not only with phosphate, like all organisms on Earth grow, they need that phosphate, but they can also grow under phosphate-limiting conditions where there's virtually none there, and potentially suggesting that in the presence of arsenic, arsenic is related to phosphorus in the periodic table. It's got the same atomic radii. And so there's the question of, is this organism surviving by taking that arsenic and using it in place of phosphate in some really important molecules? Now, that being said, that speaks to the things that we keep talking about, is about keeping the search general enough. It absolutely sticks a little wedge in our understanding, and it makes us realize that we don't know enough, even now, about our own life to categorically be able to predict what we should be looking for there. I mean, we've got good ideas, we have a strategy, but we're always learning new things, and I think that that's what that study is really highlights.
Thank you. Last question, really.
Sorry about that. I was curious, what steps are you taking on the current and future missions that you weren't necessarily taking with Viking about avoiding contamination of Mars with Earth-based microbes?
Well, you've been doing contamination control,
okay, so there is what's called the planetary protection policies that are in place, and those are guidelines for what we need to do to prevent bringing microorganisms from Earth to Mars. And those have been vetted out by lots of scientists and everything. It's the best that we can do to try and prevent embedding organisms into the Martian environment. And so that takes care of the microorganism side of things. With an instrument on board that is specifically looking at organic molecules, we have to take that one step further, and we have to make sure that we know what organic molecules we take with us and what might happen to those organic molecules, in other words, what they might turn into once they get to Mars. So the instrument itself is super clean. It goes through every single component, goes through multiple levels of cleaning. Cleaning. It's a long, long cleaning process. The rest of the instrument is also have certain specs that have to be met for keeping it clean. But the other thing that we're doing is cataloging all of the organic materials that are actually going on there. So for instance, Teflon type coatings are used often for insulating wires. We have logged all that type of information. You know, that there's different, I think there's lubricants in the actuators or something like that. Is that right? The dry lubricants. Those types of things, all that stuff is cataloged and we have a record of it. So what'll happen when we get to Mars is there is what's called the organic check material. They're basically bricks that are super clean with the exception of 1 or 2 compounds that we put in there. And we'll send the drill over. The drill actually goes into the brick, drills it like it's a sample, and then we process that sample like it was any other rock on Mars. And that is going to tell us what is the background level of contaminants in the system right then and there on Mars. So we will know if there's something there. And if we see it in that, then we know that if we see it in a sample, it was something we brought with us.
Well, listen, I want to thank everybody. Excellent job. If we could have the next slide, please. We have had the privilege of having an exploration program that has brought us from being able to follow the water and determine at least that Mars has the potential for having had life. And we're now on the track to figure out if that has ever happened. And it's going to be difficult, it's going to be a challenge, but it's going to be a wonderful adventure. And one of the things that we want to do is bring you all with us as we go on this exploration. So please look at these websites. You can see Curiosity being built. You can see what we're doing in the Mars program. You can actually join a student imaging program where, in fact, you can recommend places that you want pictures taken of Mars. Please go there and join us in this fun. And I want to thank everybody, and in particular, I want to thank the Air and Space Museum and NASA for sponsoring this event. Thank you.